Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome to the next class of CS131 discrete structures. I'm talking about graphs and graph theory. And in this particular lecture, I'll be talking about Hamilton graphs and Hamilton paths and Euler paths. That is a very specific problem, and it deals with a very specific and very generic issue, I think, with graphs and how graphs are handled. So far, you have basically discussed most of the things related to graph terminology and related to connectivity and other properties of graphs. In this particular section, which is section 10.5 of your book, which talks about Hamilton and Euler paths, I'll be talking about a very specific property that exists in graphs and how we can measure it, and the different theorems that are related to these both of these particular topics. So let's start with the section 10.5, and I'm going to share the screen with the PowerPoint slides. And here we can then discuss the various things about Hamilton and Euler paths. So let's say if we start with this very simple problem statement for circuits. Let us suppose that you are given a graph G, which has got a vertex at V and an edge at E. Then there's one very specific question that might be asked, or that might be needed, or that might be the requirement of the problem that we are trying to solve. And it's a very generic question. Can we travel along the edges of a graph starting from a particular vertex and returning to it back by traversing each edge of the graph exactly once? So this basically means that each edge of the graph is traversed exactly once only, right? And this basically means that all edges are traversed, number one. Number two, that each edge is traversed exactly once only, right? So this is a particular problem that you might be facing. You have to use all edges and you have to use them exactly once, right? And not more than once. So another problem, there's one kind of problem where each edge has to be traversed exactly once, but I think a more advanced problem maybe, or a more complex problem would be that given a graph G with vertex set V and edge set E, can we travel along the edges of a graph starting at a vertex and returning to it while visiting each vertex of the graph exactly once? So the previous problem was about the edges. This one is about the vertices. And we have to return back to each vertex exactly. We have to visit each vertex exactly once. So if you take an edge and visit a vertex, then you cannot actually, and once you're out of it, you cannot actually come back to that vertex. That vertex has already been used or visited. So the thing is that although these questions may seem to you to be very, very similar, the first question, which asks whether a graph has an Euler circuit, can be easily answered simply by examining the degrees of the vertices of the graph. So if the graphs if the whole graph has all even degrees, then possibly the first question, which basically says that can we traverse each edge exactly once, that can be answered. That yes, since the vertex degree is even and all vertices are even, hence we can basically have an Euler circuit or something, right? So the first question, which talks about if in a graph, if we can travel along the edges of a graph starting at a vertex and return to it by traversing each edge of the graph exactly once, if this is true, then there is an Euler circuit that is possible. The first question that is being asked here is about the Euler circuit. So the first question is about Euler circuit, and the second question automatically then is, so for the first question we just need to examine the degrees of the vertices, and for the second question, which asks if we can whether a graph has if we can traverse starting at a vertex and return to it while visiting each vertex. So here it's vertex, here it's each edge, right? So if it's about a vertex, then it's basically what we call a Hamilton circuit. So the second question which is asked is that if the graph contains a Hamilton circuit, is of course the first one is quite simple to answer, but the second one, the Hamilton circuit one, like I said earlier, is quite difficult to solve for most graphs. And we'll see why that is the case. So let us begin with some of the definitions. or some of the inquisitive questions that were asked in the previous slide. So what is Euler path and what is Euler circuit? So an Euler circuit in a graph G is a simple circuit containing every edge of G. So each edge that is present in a graph G is contained in this particular circuit. And since it's a very simple circuit, however, with the property that it contains all the edges in G is what makes it an Euler circuit. So an Euler path, on the other hand, in G is a simple path. And we have already discussed the difference between path and a circuit or cycle, and a path or a walk. So an Euler path is a simple path containing every edge of G again, right? So the difference between Euler circuit and Euler path is that an Euler circuit is by default an Euler path as well. However, each path need not necessarily be an Euler circuit, because for a circuit you need to start and end at the same point, but for a path you can start and end at different points. However, an Euler circuit is by default an Euler path. So for example, let's take this example. This is one graph G1. Can you start and can you end at the same vertex while you're basically using all of the edges present in this? So for example, let's start at A. Let's start at this point A. And here from A, we notice that you can actually take A, B, you can use this edge, then you can use this edge to reach E, then you can use this edge to reach D, then you can use this edge to reach C, then use this edge to reach E again, and finally this edge to reach back to A. So in this case, we can actually take any vertex and you'll basically be able to return back to the same vertex using some possible path, right? So there exists at least a path from which you can actually start and end at the same vertex. So this is a particular graph. The graph G1 contains an Euler circuit. So it contains an Euler circuit if we start in A and we can end back at A. So let's talk about this one now. In this case, again, let us say that we start from E, and we'll notice that, for example, let's say if you start at E, let's go to D first, D, and then to maybe A, and then to maybe to reach back to E. Then if you can take E, you can take C, then you can reach B, then you can reach C, and finally you can reach E again. So while you are starting and ending at the same point, however, the problem here is that in this particular scenario, there are two edges that were not used. So G2 would be very hard to contain an Euler circuit, and we'll see the reason why, because the degrees of each node here. So for example, degree here is odd, it's 3, this one is 3, and this one is 3, and this one is also 3. So if you have got more than one edges with odd degrees, we'll notice that it will not be possible to find an Euler circuit. However, you might be able to find Euler path, but in this case, even that is not possible. So let's start with the next example, which is basically, let's say this one for G3. In G3, again, you'll notice that we can start at maybe, let's say A. So let's take this path, A to C, C to D, D to A, right? And A to B, B to D, D to E, and E to B again. So G3 contains an Euler path because we have used all the edges. However, we started at A and we ended up at B. So in this case, there does not exist an Euler circuit, at least in this particular scenario, right? But an Euler path does exist between A and in the graph. So an Euler path exists, but an Euler circuit does not exist, and we'll see different things here. So the graph G1 has an Euler circuit. Graph G1 has an Euler circuit, right? I said before. So this one has an Euler circuit, which is A, E, C, D, E, B, A. Again, you can use the edges and you can see the same thing. Neither of the graphs G2, so neither this graph nor G3, neither of the graphs has an Euler circuit. Both of them do not have Euler circuit. G3, as I just showed you, has an Euler path, namely A, C, D, E, B, D, A, B. So that's the path that is shown here. And G2 does not also have an Euler path. And it's understood that if you have an Euler graph, then you automatically have an if you have an Euler circuit, then you automatically have an Euler path as well. So let's take these directed examples, H1, H2, and H3. And in this case, it's going to be a very interesting thing. For example, if you take, for example, let's say H1, neither has Euler graph nor does it have Euler paths, right? Because you can start from A or any other place and you'll basically be missing. This one is only incoming edges, you cannot start here. This one has two outgoing edges. Let's take this path, then this one, then this one. However, now you're getting stuck at B. On the other hand, let's take this example. So let's say that you start at E. So you take this path, you take this path, you take this path, you take this path, right? Then this one, then this one, then this one, and finally this one to reach back to E. So this does contain an Euler circuit and also an Euler path automatically. On the other hand, let's just discuss this one. So let's say that we start at C, move down here, then move back to C, then move here and move back to B. So now this contains an Euler path, but it does not contain an Euler circuit. So the graph H2 has an Euler circuit like we thought exactly. So this one, graph H2 has an Euler circuit, and that is what is mentioned here. It starts from A and goes on till goes back to A. This is an Euler circuit. Neither H1 nor H3 has an Euler circuit. Both of them do not have an Euler circuit. However, we know that H3 here has an Euler path, namely C, A, B, C, D, B, for example, starting from C, like I did earlier. And H1 does not have an Euler path or an Euler circuit in both cases. So again, this is something that I kind of went through manually, and I can come up with some of the I can basically show that if a graph contains or does not contain an Euler path or an Euler circuit. However, the basic question is, when does a multigraph contain an Euler circuit? And here we're talking about multigraph as in an undirected graph that can have multiple edges. A connected multigraph with at least two vertices has an Euler circuit if and only if each of its vertices has even degree. So if each and every single vertex of a graph has an even degree of a connected multigraph has even degree, then it must have an Euler circuit. So for example, let's take this one. The degree in each of this is 4, 2, 2, 2, 2, and 2. So this must contain a connected, this is also a connected multigraph. So this must contain an Euler circuit, right? So let's start with A, right? A, F, C, D, E, C, B, A, right? Or take anything. So this will contain an Euler circuit because the degree of each of its vertices is even. Let's talk about this one. Again, the degree of each of these vertices is 2. So this will contain an Euler circuit as well. So what about this one? So here we can say that the degree of this vertex is 3. The degree of this vertex is basically 5. And if you contain at least one circuit that has odd degree, then basically it will not contain a Euler circuit at all. So just by looking at the vertex C or vertex B or vertex D or vertex A, right? So if you look at all of these vertices, it ensures that there is no Euler circuit present in this particular statement. Actually ensures that there's no Euler circuit that is present in these graphs. So how do you construct Euler circuits? What's the algorithm here? And this is something that I really wanted to, or I have skipped so far mainly because I thought that you did not know programming. But since now you're aware of programming and you already are aware of while functions and other statements, so I'll try and explain this particular algorithm to you in this lecture. So let's start with the how do you construct an Euler circuit? The procedure is simple. The name is Euler, right? The input is a graph G, which is connected multigraph with all vertices of even degree. So all vertices are basically even. Otherwise, you should not construct Euler circuit at all. So what's the basic circuit? A circuit in G beginning at an arbitrarily chosen vertex with edges successively added to form a path that returns to this vertex. So a circuit that we finally want to return is basically the main circuit that starts with at an arbitrarily chosen vertex. And then edges are constantly added to this vertex as well as more vertices, so that ultimately you basically form a path that returns to this particular vertex. Again, Since it's a circuit, it has to return to the same vertex. So H is now or temporary graph G with the edges of this circuit removed. So again, in this particular case, what you do is you come up with a subgraph H in which all the edges are removed and only the vertices are kept. So now while H has edges, um, so while the graph H still has some of the edges, in that case, you construct a subcircuit, which is basically a circuit in H that begins at a vertex in H that is also an endpoint of an edge of a circuit. Finally, what you do is you add, you basically have the update the subgraph H in a way that H with edges of subcircuit and all isolated vertices removed. So anything that is a subcircuit will basically be kept, as well as all the isolated vertices will basically be removed. So whatever is being isolated from the subcircuit will be removed. And at the end of the day, until H will have edges remaining. So actually this is basically H, you initialize H with H is equal to G with the edges of whatever is the basic circuit, it will basically be removed. And you'll basically be adding the remaining edges that are present in H will be kept for further analysis. And until H has edges, you keep on getting subcircuits, and you basically, whatever edges is being pointed out, whatever subcircuit is being pointed out, you'll add it to the circuit. So circuit with subcircuit inserted at the appropriate vertex. So subvertex is being being inserted continuously into the circuit. And with each of these insertion, the subcircuit edges are basically removed, and also anything that gets isolated in terms of vertex is also being removed from H. And this will keep on running unless or until H has any of the edges that remain. So as soon as all edges in H are removed, we basically get a circuit, and the circuit is basically in whatever order you are adding your edges into it will be your circuit. That order gives you the corresponding circuit, the Euler circuit. And this algorithm is really simple. All you're doing is first you find a circuit within it, then you basically remove the edges of the circuit from H, basically where H is just a duplicate of G, and you remove those edges and isolated vertices, and then you just run in a loop where you are going to keep on finding subcircuits, keep on removing its edges from the main graph H, duplicate graph H, and you basically add these definitions of circuits at the appropriate vertices within the subcircuit, right? So this is the whole algorithm. I'm not going to give you the algorithm and ask you to apply it. However, we'll see in an example now how this algorithm is applied. You don't need to make it up on your own, but maybe you need to know how to use this algorithm to come up with a proper Euler circuit, right? So let's take an example. Many puzzles ask you to draw a picture in a continuous motion. So for example, you have to draw a picture connecting some points without lifting a pencil, so that no part of the picture is retraced. So you cannot lift a pencil, nor you can basically just move back on the line again. So you can neither repeat the edge nor basically lift the pencil and start randomly at another place. We can solve such puzzles using Euler circuits and paths. Of course, we can use Euler circuits or Euler paths to solve these kind of problems. So for example, Muhammad al-Khwarizmi, the great father of algebra, actually has a specific contribution here. And he came up with this particular problem, which we now call Muhammad's scimitars, right? So Muhammad's scimitars is something that looks like this. And the idea is, can we draw these scimitars in a particular way where the drawing begins and ends at the same point? So you start at a particular point and end at the same point. And for this, we're going to use algorithm 1 to construct an Euler circuit. And here's the idea. First of all, you must note that there is no vertex here which is degree odd. And hence, since all the vertices of this particular graph are even degree, hence the graph G will have an Euler circuit. How do you find that? And that is exactly the thing that is mentioned here. So we use an algorithm 1. So first we basically start with the first circuit. Let's say the first circuit that is formed is A, B, D, C, B, E, I, F, E, A. So A, B, notice the edges that we are going to use. A, B, right? So A, B, then B to D, D to C, and C to B, right? So this one is being used, and then B to E, this one, and E to I to F, and then F to E, and E to A. So we are starting and ending at the same vertex, and this was just an arbitrary path that got chosen where we used some edges. So the subgraph H will be obtained by deleting the edges in this circuit. So each of these edges that are marked red are now deleted, and the ones that are remaining that are not marked are the ones that are remaining in this particular graph. You must note that we started from A, and we have basically formed a sub-circuit in which we have used some particular edges, and we have now reached the point where we basically have the remaining edges present with us. So next is that we have obtained the subgraph H by deleting all these edges, and also the vertices that are basically isolated when these edges are removed means that A, for example, C are completely removed. A, C, B, E, and A, C, B, E are removed, while D has an edge remaining. So D, F, I, J, H, G, K, D remain. So splicing this new circuit into the first circuit. So so the next thing that we now have left is basically we need to find another circuit, and let's start at D, and let's move on with this. So let's start from here, D, G. So this edge is now removed. For this, I'm going to write 2. Yeah, so I use DG, then G to H, then H to J, J to I to H, and H to K, K to G, G to F, F to D, and that's basically started from D and end up to D by using these edges. And once you end up in D and H, after forming this particular circuit, we have used all edges in G. So after you form this, you have actually used all possible edges in G. However, when you splice this new circuit into the first circuit, at the appropriate place produces the Euler circuit. So you need to put this new circuit into the previously formed circuit, which was this one. So this was my circuit 1, this was my circuit 2, and after I get both my circuits ready, I need to splice them or put them together. And then the way would be, for example, A, B, D. So A, B, D, and then you can basically go on G, H, J, I, H, K, G, F, D, right? And then go on with C, B, E, I, F, E, A. That's the possible splicing, since this was starting from A and this is starting from D and ending at D. So you need to put this particular graph into the corresponding place over here, which is here. So here I can basically put in my circuit right here because it starts and ends at D and uses all the edges. So now my new graph, my spliced up graph, my combined graph after putting it at the appropriate place is going to look like ABD. So ABD from here. And then from here I can continue on with G, H, J, I, H, K, G, F, D again. So back at D, right? And then I can continue on with C, B, E, I, F, E, A. And this gives me the Euler circuit. And actually, if you draw it like that, the circuit gives a way to draw the scimitars without lifting the pencil or retracing part of the picture at all. So this is this problem of finding the Mohammed scimitars using a sample Euler circuit is very much possible by using this particular algorithm, and I've clearly applied this for you. So you must know how to apply this algorithm. I'm not going to ask you what that algorithm is, since you're not very comfortable with algorithms yet. However, you must know how to apply this on a given circuit. For example, in this case, I took the Mohammed scimitars. So there's another theorem that states that a connected multigraph has an Euler path, but not an Euler circuit, if and only if it has exactly 2 vertices of odd degree. So an Euler path is possible if it contains exactly two vertices of odd degree. But if it does contain exactly two vertices of odd degree, then it will not contain an Euler circuit whatsoever. So for example, if you look at this particular scenario, we notice that D and B are two vertices with odd degree. So in this case, we start from any place. Let's start with A, D, C, B. Sorry, we cannot start from A. We have to start with an odd vertex. So let's start at D. DA, AB, BD, DC, and CB. So this will contain, or we've used all the edges, and you will note that after we've used all the edges, this one is odd, this one is odd. So we have came up with an Euler path because we started at D and ended at B. But in this case, it will not contain an Euler circuit because the start and end points are always different. So let's take this scenario. So in this case, actually, you have got one vertex with odd degree, two vertices with odd degree, right? No, sorry, this is not odd. This is not odd. So I need to remove this one. So this is not odd, right? This is even. This is even. This is even. This one is odd. And this one is again even. So it has now got two vertices with odd degree and 1, 2, 3, 4, 5 vertices with even degree. And in this case, again, start from an odd vertex. So for example, let's start from here. This should contain an Euler path, but not Euler circuit. So we'll see how that is possible. So we take this one, start from B, go to A, G, come back to B, go to C, go to G, go to F, come back to C, then go to D, go to F, go to E, come back to D, and we have used all the edges but not returned to the same point. So this will also contain an Euler path. Let's take this one now. Let's calculate the vertices degrees. So now I notice that this one is odd, right? So it has got 3. This one is odd. This one is also odd. So a lot of them are odd degreed vertices. Hence, this will not contain an Euler path nor an Euler circuit at all. These one do not contain Euler circuit, but they do contain Euler paths. This one will neither contain an Euler path nor an Euler circuit. And why is that happening? We'll see. That was because this one does not contain exactly 2 vertices of odd degree. It contains 6 vertices of odd degree, or even more. 1, 2, 3, 4, 5. Yeah, so this one is even degree, but the rest one are all odd. So G3 does not contain any Euler circuit or Euler path. So what are the different applications of Euler paths and Euler circuits? I showed you one particular problem. However, many other problems will desire, or it is desirable to come with an Euler path or Euler circuit to solve some practical problem. For example, many applications ask for a path or circuit that traverses each street in a neighborhood, each road in a transportation network, each connection in a utility grid, or each link in a communications network exactly once. So you have to traverse each network exactly once and not more, and that is a particular problem of Euler path. So finding an Euler path or circuit in the appropriate graph model can solve such problems. Of course, you need to come up with an Euler path or Euler circuit. For example, if a postman can find an Euler path in this graph that represents the streets the postman needs to cover, this path produces a route that traverses each street of the route exactly once, and he'll not waste his time on coming back or using the same path again. So for a postman, it will be more efficient to use the Euler path or Euler circuit. If no Euler path exists, then some streets will have to be traversed more than once, and that is something that he needs to avoid. The problem of finding a circuit in a graph with the fewest edges that traverses every edge at least once is known as the Chinese postman problem. So the problem in here is to find a circuit in a graph with the fewest possible edges that traverses every edge at least once. So of course you have to use a few that traverses every vertex at least once. So this is something that I've written by mistake here. This is basically traverses every vertex, and this is known as the Chinese postman problem in honor of the Guan Migu, who posted it in 1962. So among the other areas where Euler circuits and paths are applied is in the layout of circuits in network multicasting and in molecular biology as well, where Euler paths are used in the sequencing of DNA. So if someone among you might be going on to study the course of bioinformatics, there we'll be discussing the problem of Euler paths and Euler circuits in a lot more detail, in particular when I'll be talking about, if I'm the one who's teaching it, of course, if I'll be talking about sequencing of DNA and the problems associated with it. So this is something that is one of the applications, one of the tasks there. In particular, they're commonly known as De Bruijn graphs, and we'll see the relationship between memory and other stuff here. But this is very clear that Euler paths and Euler circuits are have a lot of applications in a lot of different fields. So let's talk about the other topic that is supposed to be discussed in this particular lecture, which is Hamilton paths and Hamilton circuits. A simple path in a graph G that passes through every vertex exactly once is called a Hamilton path. And a simple circuit in a graph G that passes through every vertex exactly once is called a Hamilton circuit. So a path that does it is Hamilton path. A circuit that does it is basically Hamilton circuit. Notice that it passes exactly once through every vertex. So there may be edges that are not used. However, every vertex is visited exactly once only. So that is the simple path x0, x1, so on until xn minus 1, xn in the graph G, which consists of vertex at V and edge E, is a Hamilton path. If the path V contains exactly all of these vertices x0 to xn, and there's no vertex that is repeated in this particular path, and hence the simple circuit, if it's a path, then nothing is repeated, and it is basically a circuit if it starts and ends at the same vertex. And basically it uses all of the vertices in the graph. If that is true and it returns and ends at the same vertex, then it is called a Hamilton circuit. So let's take some examples, I think, before we move on. And this is a particular, let's say, a football-like structure, and this is represented over here in a particular manner. And we have to discuss if it contains a Hamilton circuit. We notice that it does contain a Hamilton circuit. The lines in blue actually mention, for example, if we start from this point, right? So we can take I'll take the same example over here actually. So start from this particular point, you're going to use this edge, then it uses this edge, then it uses this edge, right? Then it uses this edge, then it uses this edge, then this edge, then yeah, so then this edge, then this edge, then this edge, then this edge, right? And then this edge. So you are not visiting a vertex again, you're always visiting vertices that had not been visited in the previous run. So now you go back over here and notice that the end goal should be to visit each vertex over here, like I'm doing. So finally you basically reach this point, and this is your starting point again. So you reach back to the same vertex. Notice that in this particular example, there were some edges that were not used at all. For example, this one, this one was not used. However, each vertex was visited, and the Hamilton path or Hamilton circuit is all about visiting each vertex exactly once, except for the last vertex, which is also your starting vertex as well. If that is true, then this becomes the Hamilton circuit. Otherwise, if you end up on a different vertex than a starting vertex while having visited each vertex exactly once, then this is a Hamilton path by definition. So let's take some more examples. In this case, does this circuit contain a Hamilton circuit or a Hamilton path? Well, the idea is clear. So for example, use this edge A, E, D, C, C, B, and finally back to A. So this does contain a Hamilton circuit. What about this one? So this one will, for example, use this edge, this one, and this one. So yeah, so sorry, not this one, because then you reach back to B, which is not your starting vertex. However, you don't want to use it. So this one contains a Hamilton path because we used all the four vertices. However, it does not contain a Hamilton circuit because the starting point and ending point of this Hamilton path are different. So this contains a Hamilton circuit. This contains a Hamilton path, like I showed. What about this particular scenario? Well, in this particular scenario, you start from any point. Let's start at F, right? F to E, then to G, then to B. And here is the problem. If you take this particular vertex A, actually, you cannot actually move out and come back to B. On the other hand, if you take the vertex C, then we'll never be able to visit A since A has only one path available from B. So in this case, neither a Hamilton circuit nor a Hamilton path. And that is what is exactly written over here. So how do you determine if there is really any simple way to determine whether a graph has a Hamilton circuit or a Hamilton path? Well, the answer is it might seem actually that as simple as it was to get answers for Euler circuit in a very which seemed a very similar question actually, since the answer was very there was a simple way and a very clear answer there. At first it might seem to you that there is also an easy way to determine this. However, there are no known simple, necessary and sufficient criteria for the existence of Hamilton circuits. So there are no simple, necessary and sufficient. Necessary means those that are met for this, and sufficient means that if they are met, we are sure that the Hamilton circuit must exist in the graph. And there are no such known, simple, necessary and sufficient criteria. However, there are many theorems that are known that give sufficient conditions for the existence of Hamilton circuits. So if those conditions are met, we might say that they may contain Hamilton circuits, but the Hamilton circuit itself it's not an easy thing to find out. So again, absence of these particular sufficient conditions can be used to show that a graph will have no Hamilton circuit, and we'll discuss these in a minute. So a graph with a vertex of degree 1 cannot have a Hamilton circuit. So if in a graph there's a vertex with degree 1, it cannot contain a Hamilton circuit, because in a Hamilton circuit, every vertex is incident with 2 edges in the circuit. So this is one of the particular property. For example, this graph cannot contain a Hamilton circuit because it's at least one vertex with degree 1. On the other hand, this one may contain a Hamilton vertex because at least there is no vertex with degree 1. Although again, it will not be it will again not contain a Hamilton circuit, and we'll see why. So if a vertex in the graph has degree 2, then both edges that are incident with this vertex must be part of any Hamilton circuit. So if there is exists a vertex with degree 2, then both edges that are incident with this vertex must be part of any Hamilton circuit. So when a Hamilton circuit is being constructed and this circuit has passed through a vertex, then all remaining edges incident with this vertex other than the 2 used in the circuit can be removed from consideration. So when you are constructing a Hamilton circuit and the circuit has passed through a vertex, then all the remaining, of course, because you are not going to visit this particular vertex again. And if that is true, then all other edges that are all other edges and the 2 that are used in the circuit should basically be removed. So in this particular scenario, actually, we noticed that this graph contains a Hamilton path, but it does not contain a Hamilton circuit because you cannot return back to the same vertex. So a Hamilton circuit cannot contain a smaller circuit in it. Notice this point. This is important, and this is the exact theorem or exact point property that can be used to point out that a Hamilton circuit cannot exist for the graph H, because it contains a smaller subcircuit like that, and hence a Hamilton circuit cannot contain a smaller subcircuit. And this is the exact property which was used to determine the Euler path or Euler circuit. However, in this case, it cannot be used because if you notice here, if it contains a smaller circuit, then we will basically be reusing the same vertex again, and that is a particular property that is not desired, or that is not possible, that is improbable for a Hamilton path or Hamilton circuit. Using the same edge is not allowed, simply. Sorry, using the same vertex is not allowed, and hence this will become problematic. So let's talk about a complete graph. A complete graph Kn has always a Hamilton circuit whenever n is greater than equal to 3. So whenever the value of n is greater than equal to 3, it will always contain a Hamilton circuit. Then there's a theorem which we call, and I mean the previous one is absolutely clear. So if you have got multiple edges and every edge is connected to every other edge, then it will contain a Hamilton circuit by default. It's not a rocket science. It's very simple. You just use an edge to traverse from any vertex to any other vertex, and basically whatever vertex you use, you can simply remove it from your you can put it into your use set, except for if it's your initial vertex. In that case, you might want to come back to it at the when you reach the last vertex. From there you can come back to the first vertex, and this constructs a Hamilton circuit. So this is very clear. So let's talk about Dirac's theorem. And Dirac's theorem simply states that if G is a simple graph with n vertices, with n is greater than or equal to 3, so number of vertices in a graph are equal or more greater than 3, and G is a simple graph, such that the degree of every vertex in G is at least n by 2. So the degree of each vertex has to be at least n by 2. If you have got a graph with 10 vertices and the degree of each vertex is at least 5 or more, then in that case G has a Hamilton circuit. Again, the more degrees you have in a complete graph, for example, the degree of a graph is 10, and that's very easy over there. But it's kind of a theorem that states that for most cases, or for almost each and every case really, wherever the degree of each vertex, the vertex with the lowest degree is greater than n by 2, and then it will contain an Hamilton circuit. However, the vice versa is not necessary. That, you know, if G is a simple graph with n vertices and the degree of those degree of some of the vertices may be even less than n by 2, and it may still contain the Hamilton graph, a Hamilton circuit. However, the condition that is mentioned here is that if a graph, if a graph does contain each the degree of each vertex in the graph is actually equal to or greater than n by 2, then it will for sure contain a Hamilton circuit. Similarly, we have got a theorem which we call the Euler's theorem, and it states that if G is a simple graph with n vertices with n is greater than or equal to 3, such that degree of the vertices v and u are greater than or equal to n, so number of vertices, for every pair of non-adjacent u and v. So if you pick up any non-adjacent u and v and the degree is greater than or equal to n, then the graph G will also have a Hamilton circuit. So even if you have got some of the nodes whose degree is less than n by 2, but the degree of any non-adjacent pair of vertices u and v is greater than equal to n, then you know the graph will contain a Hamilton circuit. And these are just theorems that you need to kind of know and how to apply. However, note that both the Euler's theorem and the Dirac's theorem actually provide sufficient conditions for a connected simple graph to have a Hamilton circuit. However, these theorems do not provide necessary conditions. So if these conditions are true, then it's sufficient. However, these conditions are not, they do not provide necessary conditions. You know that if this is true, this is not true, then the Hamilton graph will not exist. And that is basically saying that for example, taking the graph C5, cycle 5, right? So, you know, C5, it has a Hamilton circuit, but it does not satisfy the hypothesis of either Euler's theorem or the Dirac's theorem. So even if absence of these does not necessarily mean that it will not contain a Hamilton circuit. And on the other hand, the best algorithms that are known for finding a Hamilton circuit in a graph, or determining that, you know, no such circuit actually exists, have exponential worst case time complexity. And when we'll talk about time complexity, you'll understand what I mean by this particular line over here. So they cannot be found in a normal exponential in a normal time complexity in a possible linear or quadratic time worst case time complexity. And that is why you know, it's not an easy task. We'll know that what the NP hard problems are, and this is one of those kind of problems where the solutions have got an exponential worst case time complexity. So finding an algorithm that solves this problem with polynomial worst case time complexity would be a major accomplishment, because it has been shown that this problem is NP complete. And hence this is something that you probably need to, you don't need a heuristic solution here, you need an exact solution. And if you can find an algorithm that actually solves this problem with polynomial worst case time complexity, would be a major accomplishment. And hence it's not an easy task. People have tried it for many decades now and it has not worked for them. So I'm not saying that, it's not possible. I'm just suggesting that if you think about it, if you are really good, and if you want to learn a lot more, and if you want to be good in applications, think about this problem and try to solve it in a with a polynomial worst case time complexity. And if you're able to do that, I think that would be one of the major accomplishments. You might be given a really good award, even a good scientific award even for it. So, but anyway, this is not an easy thing to come with the right algorithm, and hence we are not giving any algorithm in this particular course, right? So then let's come up to applications for Hamilton circuits. Why are we studying Hamilton circuits? Well, Hamilton paths and Hamilton circuits can be used to solve practical problems. For example, many applications ask for a path or circuit that visits each road intersection in a city, each place pipeline intersect in a utility grid, or each node in a communication network exactly once. So if it's about nodes, if it's about vertices, then Hamilton paths and Hamilton circuits is the way to go with it. So finding a Hamilton path or a circuit in the appropriate graph model can solve such problems. Of course, you need to convert them into a graph problem, and then you can apply the Hamilton path or Hamilton circuit to analyze this. And of course, one of the commonly known problems, the traveling salesperson problem, or TSP, which is also called the traveling salesman problem in the older literature. It asks for the shortest route a traveling salesperson should take to visit a set of cities exactly once, right? And of course, you don't want to come back to the city because that is going to just enlarge your route. And hence, you want to traverse from one place to another, and that is basically what we call a traveling salesperson problem. And I think in this particular scenario, it reflects more of a Hamilton path, because there is a starting city and then there's a final city where you want to visit each of the group of cities within the graph. So this problem reduces to finding a Hamilton circuit in a complete graph. So if it's a complete graph such that the total weight of its edges is as small as possible. The limitation here is to find a Hamilton circuit in a complete graph where the total weight of its edges is kept to a minimum. And that's why it's a traveling salesperson problem. You want to minimize the number of the distances traveled and minimize the weights of the edges. And we'll see it in the next few lectures as well. So that brings an end to section 10.5, where we basically talked about Euler paths and Euler circuits and Hamilton paths and Hamilton circuits. These are two very important topics in graph theory, which have got applications in a wide variety of fields, as we saw. The main thing that we learned from this particular lecture is that for Euler path and Euler circuits, which is a relatively easier task to find, the main idea is to visit each edge exactly once. For Hamilton paths and Hamilton circuits, the main idea is to visit every vertex exactly once. And while both of them seem very similar, and we do have got very easy algorithm as well as a very straightforward method to know if an Euler circuit or Euler path exists in a particular graph, the same is not true for Hamilton paths and Hamilton circuits, despite the similarity. And it's not an easy task to find Hamilton circuits or Hamilton paths. However, there are some conditions which, if met, maybe they may indicate if the graph contains a Hamilton path or Hamilton circuit. However, so far it has been done manually, or the algorithms that do exist are of exponential time complexity and NP complete, and hence these are some things that we always are trying to avoid to the best of our knowledge. So now let us shift to chapter 10, section 10.6. where we'll be talking about shortest path problems. That is going to be in the next lecture. I hope you've learned something about graphs and about Hamilton and Euler paths and Euler circuits and Hamilton circuits in this particular lecture from me. Hope to see you in the next lecture of CS131, which will be about the shortest path problems. So see you in the next lecture. Take care.